Yo, what up? Welcome to Made by Ozzy. I'm Ozzy, and we're lucky enough to have Copper joining for the video today. Hey, quick shout out if you're watching, Devils, you are the man. All right. So today we're going to continue moving our project forward. We're turning this FPGA development kit into both a cryptocurrency miner and a GPU. To render graphics. So today what we're going to do is build the receive buffer. Finally, over the last few episodes we've been building up an RS232 communication channel. So we got receive working for 1 byte, we got transmit working for 1 byte, and today what we're going to do is finish up with a buffer. We're going to receive 3 bytes. And so we're going to build it in a way, I'm going to keep it only at 3, and let me tell you, a few reasons why I'm making it so simple and so small. This is a really simplified receive buffer. In order to actually use it for anything, we're going to have to add more functionality, but I really just kind of want to show how you would do this, and then put a nice little button up on this FPGA Essentials series, so we could start getting some real fun stuff, some really serious crypto. Once we can circle back to putting it onto the FPGA, we're gonna have to add some more stuff to the buffer. So today I want to do 3 bytes specifically because I have 6 7-segment displays. I need 2 of those to display 1 byte if I use the hex decoder. All this stuff we've written on the channel in the past few videos, so if any of this is a mystery, just go back, watch a few videos, and then of course everything is already live on the GitHub, so if you want to just get the code, you could always just clone the GitHub, and that's fine too. So I want to show 3 bytes just so I can actually see them on my 7-segment display without any hassle, and it's nice and small, and we're going to make it based off of variables and stuff anyway, so we could always it's very easy to grow into more bytes in the future, no problem. So everything that you're going to see on the video today is already live on the GitHub. You could go, clone it, get up to speed immediately. But right now, let's go ahead and get started coding it. Okay, so just picking up, so in the last one, I made this OneShot thing and made it the top level entity. So I need to go open my normal BDF. There it is, there's copper.bdf. And I'm going to set this back to the top level entity. And all is right in the world again. Okay, so let's go ahead and make a new verilog file. Okay, module, and let's name it receive buffer and rev a. I'll probably change it. Figure that out in a second. And module, and go ahead and save this here in library. No, we're not going to name it that. Receive buffer rev a, right? No capital R. Yep. Okay, cool. So standard inputs, we want the clock and a reset, and then what are we gonna get in? We're gonna get in a couple things, right? So what are we gonna get from our flags here? We have an RS232 output, RS232 receive module, which has this data done flag and has data out. So we probably want both of those, right? So let's get data done, that's an input, and data out, that's also an input. I'm gonna call it data in so it's not confusing. And then this is a buffer, right? So what we're gonna receive a few of these bytes, these 8-bit values, and then we're gonna display them, and we're gonna do 3 of them, right? So buffer out. Okay, so let's define our IO. Input clock reset, and data done is also a single bit. Then data in is a 8-bit vector, so 7 down to 0 to do 8 bits, and that's data in. Okay, and then our output is going to be 24, since we got 3 bytes, so 24 bits, that's 23 down to 0. Buffer out. Yeah, let's make this a reg. Okay, so what are we going to do? Let's define a little local parameter, just some local stuff in general. Local param for max bytes here, and we're just going to set this to 3. And then so sort of stealing like what we did in this receive, we're going to have this active, instead of an active bit, we're going to have an active byte that we're going to track, but it's also going to be a a local register here. So so many bits do we need to count to 3? We only need 2 bits, so 1 to 0. Okay, active byte, that's no problem. Yeah, that looks good. Okay, so let's get our logic all set up. Always at pause, edge, clock, begin, end, always. All right, and then the reset condition, if not reset, begin, end, not if not reset, and then else, begin, end. All right, cool. And then what we're gonna do for reset, I guess we're gonna just set this to 0 and set active byte to 0. So buffer out to 0 and active byte to 0. All right, easy stuff, man. Reset's like my favorite thing to fill out because it's really hard to mess it up. Okay, so now what we're gonna do, we're gonna look for this data done input here in our normal logic condition. So if data done, begin, end. And so what's going to happen when data done is we're going to load it into the buffer here. Okay, so how are we going to do this, right? Because the position in this longer vector, this 24-bit buffer, is going to depend on this number here, this active byte. Well, first things first, we know we're going to increment active byte. So let's just get that out of the way right now. Right, but now we need something to, how are we going to figure out which bits to map that to for this buffer out? Well, it actually would just be easier if we sort of make an interim array of bytes. So let's make another local register here. This is going to be an array of bytes, so they're all going to be 8 bits long. And let's call this byte array. And what are we? And how many do we need? So we actually need 3, so that's going to be 0, 1, and then 2. That's 3 minus 1. Max bytes minus 1 is 2. So this will give us 3. So this is an array of 3 elements where each element is an 8-bit vector. And so that's how we're going to track it. And so what we're going to do is we're actually going to write stat value byte array, whatever the current active byte is, and there we're going to write data in, not Okay, so that's nice to know. I got this byte array now, and I got active byte. So what do we do when this only holds 3 bytes? So I guess if it's not data done, what we can do is sort of reset this active byte, because I want to be able to receive again, so I don't want active bytes just always count up and up and up. I want it to reset at 3. So let's make a little else condition. If it's not data done, then how about we just check the status of active byte? If active byte, I guess it just equals 3 really, because it's going to go from 0 to 1 to 2, and then once it reaches 3, that's the top, right? Begin, end. At this point, I'm just going to reset it to 0. Active byte, set it to 0. But now I have this byte array, and I need to map this back to this buffer out. And, I could do it manually, right? I know byte array 0 is going to go to, like bits 7 through 0 or something. But we have a little tool up our sleeve, right? We learned about generate. So I'm going to open this one, open that module to, sort of remind the new viewers here what generate looks like. So this is where you could use a for loop inside of a verilog to make your code a little more compact. And here we only have 3 bytes, so it wouldn't be that bad if I just hard coded everything. But I want to use generate. I want to get all the viewers here used to doing that. So I'm gonna map byte array back to output buffer. Okay, so for generate, the first thing I need is to declare a variable I'm going to use with this keyword genvar. So genvar I, and then generate with the keyword nGenerate to encapsulate the whole block. All right. Now inside this generate, I want a for loop. So let's do for I equals 0, I less than max bytes, I equals I plus 1. Begin. And remember, for loops, I have to give each for loop a name. So let's call this map bytes, and then end. For map bytes. All right. So what are we going to do here? here is where I want to sort of figure out which bits of buffer out I want to assign the current, each element of byte array. So I guess local param is a convenient way to do that. I'm going to declare a local param to calculate which starting bit I need for each element of byte array. And that's easy, right? It's just going to be local param. Well, I guess I could call it like buffer start. It's a good name. So it's going to be I times 8, right? Because that's how many bits are in a byte. But actually, let's do, I want the total, right? I want max bytes times 8. That's the total number of bits minus 1, because that's the max it could be. And let's do, I want to do left to right or right to left. Let's do minus I times 8. Yeah, that way for when I equals 0, it'll be the 0th bit, and then, or it'll be the max bit, it'll be 23. Yeah, that should work out. That'll probably look nice. Okay, so now we have a buffer to start at. Now we actually need to do something with that. So it's a register, so we always need to capture a register with a conditional block like this. Begin, end. Okay. I put 4. Always, right? Always. There we go. That makes more sense. I was like, no, I always comment always. Okay, so here we're just going to assign the buffer out, and we're going to start at this little parameter we set up, buffer start, and we're going to use this convenient little syntax, right? Because we know it's 8 bits that we're going to need, and we're going to assign it the current value of byte array at element or I. So there we go. Cool. So here, the top logic block actually is going to map the data in bus to the different elements of this byte array buffer. And then this one down here is really only there to map that byte array back to buffer out. Okay, so let's make a symbol out of this. Quick little test, see if everything works. Okay, near line 18. Oh, geez, okay. I just forgot that right there. Okay, let's try again. Okay, cool. Successful creation of a symbol. Okay, so let's go drop this into the top level module here. So just add it right in this little area. And there it is, receive buffer. Okay, same clock and reset. Control C, Control V. All right. And I already named this. Good job. All right. Got the data done flag. And I got my data in. Why didn't we do that? Control Z, Control C, Control V. All right. Now for buffer out, I can map it directly to, I guess I'm going to use that other hex one, the one I have open here. Basically this right here. Yeah, that's what I want. And I'm going to go ahead and I'll move this out. And I'll steal the hex outputs. Which is, we set this up in a previous video in this series. So I'll map them back to there. Okay, and for the meantime, I'll move this whole setup into there. And I'm not going to use the local 42-bit counter. I'm going to map this buffer out directly into here. That was the wrong thing. It was trying to capture clock and reset. Nuh-uh. There we go. All right, see if this all compiles. Ooh, not good. Okay, so can't resolve multiple constant drivers for buffer out. And so, yeah, okay, what I'm pretty sure what's happening is the fact that I'm trying to assign buffer out in this conditional block up here, and then I'm also I have a whole nother conditional block for the exact same bits over here, and these could happen at the exact same time. And there's nothing preventing that from happening, so that makes sense. So I have to remove this buffer out from up here and make my own reset condition down here to handle it. So if not reset, begin end, not if not reset, and then this is going to be captured in the else block, actually, else begin, and then end after it. and I'll also assign buffer out in the reset block, except I'm going to assign it to 0. Okay, that should do it. Let's try this again, see if we got a symbol. Okay, symbol looks good. Come over here and update that symbol. Yes, just that one there. Okay, and let's see if this compiles. Oh geez, I knew this demo RAM was gonna end up being a problem. Okay, so I changed where it was in the directory, so now it can't find it. So let's go update the project properties, add remove files here, and this is the problem here, the demo ram.qip. So I could either edit it to point it to the correct directory, or I could just remove it, and so that's what I'm gonna do. Okay, apply, okay, and let's see if this compiles now. Okay, so I didn't get all the properties right yet. Oh, I know what it is. It's only because I have it sitting in my block. I have it sitting right there. What a metiche. Okay, let's try this again. All right, successful compile. Okay, let's get this thing written out to the FPGA. So let's go Tools, open up Programmer. All right, select the file and let's write it out. Okay, so let's test this out. And I got the Python project open here. I actually tried to run it unplugged and plugged back in that little adapter. So it changed to COM4, which I verified by going here to my device manager. And now I see it's at COM4. So I changed that to COM4. And I'm going to change this K to 123, which corresponds to, I expect to see the hex characters 31, 32, and 33 on the FPGA. So let's go ahead and hit run. Okay, so what do I got? I actually have I have 33, 33, 33. I don't have 31, 32, 33. So it looks like all my my 3 bytes are probably getting overwritten by the last one. So let's go figure out why that's happening. So it's funny why this is happening is so it will assign a new value to byte array if data done is high, and if you recall, data done is actually on for an entire state, which is, you know, like 434 clock pulses. So yeah, this is on for a long time, and it's just always going to be incrementing active byte and then assigning it to basically all of byte array. So that's why actually in the last episode I built a OneShot, and this is specifically why I did it. So an easy thing I could do, you know, the graphical way, is to I could make a symbol out of that OneShot, and I could just drop it here in between. But I wanna actually declare it here in this verilog module. So I'm gonna close this RS232, and I'm just gonna leave this open to remember how to do a declaration. I'm gonna open that OneShot file. So file open, go find it in library. There it is. I just need to know the inputs: clock, reset, signal in, signal out. Okay, so let's go ahead and what do I do to declare one? I have the name of the module and then some instance that I define. Okay, so let's do it here under this generate. OneShot filter data done input. Okay, so it's called OneShot is the name of the module, and then just name the OneShot instance. Be real clear about it. So dot clock, I'm going to pass in the clock input. And with the comma, let me just double check while I'm here. Yep, dot notation, and then that works. Same thing with the reset. Dot reset, and then signal in was going to be our data done input. That's what I called it, right? Data done input. Yep. Okay, and then signal out. I guess I actually need to make another wire for signal out. And that's what I called it here, right? Signal out, yes. So let's make a local wire here. So wire, and I guess I could call it like one shot data done. Okay, and I'll just go ahead and map this to there, and close up this whole instance. Okay, that should do it. Let's hit save. Let's build this symbol again. Yeah, the PDF has changed, yeah. All right, no problems with the symbol. Let's go and update this symbol. Update symbol, yes, just that one. Okay, And let's see if this compiles. Well, it compiled, but I'm a dumb dummy. Again, another situation where as it's compiling, I'm sitting here thinking, oh shoot, I made this wire, one-shot data done, but then I didn't do anything with it. I still have the source of the bug right there, so I actually needed to change it there. So the whole process again, right? Create, update the symbol cool. Make sure I go update it here. Update symbol, yes, okay. Now let's compile again. Okay, successful compile. All right, let's get this thing written out to the board and test it out. Okay, so start. All right. Okay, let's get Python open again and write out another string. All right, let's see what we got. All right, nice. I got 31, 32, and 33. That's exactly what I expected. And then what if I change this to 4, 5, 6? This will test if that active byte reset condition works as well, because now I should read 34, 35, 36. And I just, all right, nice. Everything's working as expected. Nice. All right, great, cool. So we got the receive buffer all fleshed out. You see how you could change, we'd have to change a few things to make it work for a larger buffer, right? We have to change the local param max bytes, of course, the size of some arrays, whatever. It's not a problem, right? It's easy stuff. And I am really excited about this now because what this means is, for the savvy viewer out there, you really have the whole toolkit that you need to build basically any sort of communication onto this FPGA now. Just build this receive buffer. You know how to put different modules together, and you could take it further if you want. This is a convenient path though. For the next few videos, actually, it's going to be completely, we get to pivot into crypto, finally. So for the next few videos, actually, I'm going to take a little break from FPGAs. First thing we're going to do is build a Bitcoin miner from scratch in Python. It's probably going to take a few videos to really go over the ins and outs of the details of that, but then once we get that working, we'll be able to circle back and replace our CPU version of the hashing algorithm with an FPGA version, including the communication between the software and the firmware. And guys, I'm so excited. So excited. It's been a couple months here just to get a really core package done on the dev kit, and if you've been watching along, I really hope you like the content. I hope you hit the subscribe, leave a comment saying if you've been up to it, what you think of everything so far, and yeah, and it's a little funny too is if you've been following the videos, I shaved the day I did the channel introduction, and I have not shaved again. So yeah, this is like a few months of build up my beard. So I thought it was kind of a neat little gimmick. Now that I finally finished this series and I get to start in the crypto series, time for a fresh shave again. And my wife's been bugging me to get a haircut and everything. So anyway, I hope you enjoyed the video. Hit like, hit subscribe, help me grow the channel. Thank you so much if you're watching. I hope you all have a great day.